Anyways, I salute you all for being here. I consider myself an archivist, and what I work on archiving is human memories. And so we'll get into the technical details shortly, but I want to spend a little bit of time first saying, why do we care about archiving memories? And for me personally, the reason that I care about this comes from how I view history. So I see human history as being divided into different stages, and we advance from one stage to another by the invention of technologies that are better able to preserve information from one generation to another. And every time we invent a new technology that can preserve information, it radically catapults our society to new heights. So, originally, we have no language, we have no writing. It's more of an intuitive or animal era of history. So imagine that you never learn how to speak. Like your parents never teach you because they don't know how to speak. Imagine how that would feel, that you have these thoughts in your head that aren't even in language because you've never learned to think in those terms, and they're trapped. You can't communicate them. All you have to go on is your instincts that you're born with and your personal experience that you accumulate through your life. That's just a totally different existence that's probably so different it's almost impossible to even imagine what it would be like. At least for me, I think in terms of language, it's hard to even know what it would be like to never have a word your entire life. And I would say this is more of an animal mode of history, but then we invented language. And so language is a technology that's able to preserve information from one generation to another. Now, instead of having your thoughts trapped in your head, you can talk to someone else. So you can hear stories from your ancestors. You can hear what people 7 generations ago were talking about. You can hear about imaginary things. And so the invention of language catapulted us to the era of oral history. And that's the difference between us being animals and the difference between us being able to conquer a large part of the world. So, it's a huge advance. But just language alone and having an oral civilization is very limited in a lot of respects because you are limited to what you can actually remember, which is very low bandwidth. So the next technology that we invented to preserve information is writing, which we use writing so much it's hard to remember just how magical it is. But if someone, imagine that we didn't have writing before, and someone said, these words that I'm speaking that are ephemeral, they're gone as soon as they're said, we're going to figure out a way to carve them into stone, and they're going to last longer than a person can live. You'd say, well, you don't understand what words are. Like, that's insane, that's impossible. How can you make an arbitrary symbol mean a sound, right? And in fact, we didn't invent language all at once. We invented partial scripts that were dealing with mathematics, dealing with numbers of things. And then it took a while for people to figure out, oh, you could say anything and write it down. So if you have language and you have writing, then you have the era of written history. And that's the era that we're in right now. And it's hugely beneficial. You're able to have libraries full of things that no one person could have in their head all at once. And that's what's powered our modern civilization. But writing is still missing a lot of things. Consider what the difference is between living through a war and reading about that war in a history textbook. I would argue the majority of the value of that firsthand experience is actually lost when it's written down. Certainly it's better than not having writing at all, but you lose quite a bit. I'd say we lose most of the important bits. In particular, we lose the wisdom that we generate. It's not because wisdom is magic, it's just wisdom has such a high dimensionality to it that it can't be linearized and written down in a form and then read back. It's very hard to learn wisdom by reading. You sort of have to live it and crystallize your life experience. So if I was going to predict what the next information preservation technology is going to be, it would be the ability to capture the things that writing doesn't capture. Wisdom, firsthand experience, these sorts of things. And I think the invention of such technology will catapult us into a new era of history called the era of living history. The difference being, if you're in the era of living history, you can talk to someone who was alive and actually had firsthand experience of it. So that's the question I'm trying to answer. How can we preserve living memory? And by the end of this talk, my promise to you is that we'll have gone over these 4 pieces, and you'll see how they fit together to achieve what I think it's possible today to actually preserve living memory. And it's got 4 parts. It's got information theory, clinical science, neuroscience, and the technology of preservation. So we'll go through each of these 4 parts quickly. And information theory, we're going to learn about what it means to preserve things in a little bit more of a rigorous way. We've all got an intuitive understanding of what preservation is, and we're going to learn how to think about it a little bit more rigorously and how to think about it for things that you might not fully understand, like DNA or books written in a language that you can't read. What does it mean to preserve those things? How can you know whether you preserve those things? By the end of this talk, you'll have a better idea of that. We'll talk about some of the clinical science, which I find very fascinating, and we'll cover a surgical technique that I think is the most dramatic surgical technique in the world that most people haven't heard about. We'll go through the neuroscience. We'll briefly cover the science of memory consolidation, what our current top theories are for how memories are actually created in the brain. And then we'll round it up by talking about embalming technologies and talking about chemical preservation methods and how they're tied to spices, which you might get a new appreciation for. So let's start with information theory. So we got the I on the bottom. That's kind of a checklist through the talk. What does it mean to preserve something? All right. Well, we've all got an idea of what it means to preserve something. Those books right over there are currently doing a fine job of preserving the stories that's contained within them. But I'd like to explore this intuition with you for a little bit. And so let's play the preservation game. I'm going to say some things we could do to these books. And you raise your hand if you think that it would preserve the information of the stories that are in the book intuitively. All right? So raise your hand if you think the information is preserved. Here's the first one. We'll just leave them on the shelves for one day, and then we'll look at them tomorrow. How many do you think that would preserve the information in the books? And raise your hand if you think that it would. So you don't think that that would preserve the information. Why is that?
For one day.
For one day. So tomorrow, those books won't have their information?
Not much of a preservation, so I'd like to take.
No. I mean, will the information still be there tomorrow?
Oh, it'll be there tomorrow.
Yeah, raise your hand. Okay, so if we do it to them, does it, another way of thinking, if we do this to the books, does it destroy the information in them? Okay, so leaving them for a day, we all understand intuitively that that's not going to do anything to the information that's storing them. Okay, so number 2, we're going to burn them and scatter their ashes to the wind so no one will ever see them again. How many of you think that will preserve the information in the books? No one thinks that will preserve. No one believes that the books somehow live on, maybe. Okay, no, okay. All right, let's say that we do burn them, but we buy new copies of the books and we put them in where they were before, and they've got the same letters in them as the original books. How many of you think that operation preserves the information in the library? Yeah, all right. Not too much sentimentality in this crowd. Okay. We're going to do row 13. Now, what is row 13? It's a simple form of encryption. So you take your letter, you move it 13 spaces forward, you wrap around if you run out of spaces. So if you take the interval, it becomes Girvargini, okay? If you take Girvargini, what does that become? What do you think? The interval, right, because it's reversible. So let's say we were to row 13 all the text in all the books. Does that preserve the information or not? Everyone, you don't think it preserves the information? What do you think? What's that?
I mean, it goes both ways.
Yeah, if you wrote 13 something that's already been wrote 13, it undoes it, and you get the text back. Yeah, so it's reversible, so it's got to kind of preserve it, because it seems weird to say the information's gone when you can do something to it and get it back. Well, it clearly wasn't gone if you can get it back, right? Okay, now let's say we mixed up some clear epoxy, and we poured it on all of the books, okay? And that epoxy is going to soak into all of the pages, and it's going to glue the pages together, and it's going to render the book into a solid form of plastic, okay? And you'll never be able to open the book again. But the epoxy doesn't make the ink smudge at all. It doesn't make the ink run. In fact, it glues the ink even harder to the page than it was before. Do you think if we were to epoxy all the books over there, that that would preserve the information contained in them?
You have the right to kind of scan it, as they're doing with some of the.
Well, does the information being preserved depend on the existence of a technology or not? Does the information become preserved after you invent the technology, or was it always preserved even before you invent the technology?
You've preserved it, and the question is whether you can retrieve it.
Exactly. But it would have been preserved irrespective of the technology that exists, right? It doesn't retroactively make it be preserved because you invented a way to scan it. Okay, so, all right, great. So what's the principle here? What's the common principle behind our intuition? Why do we think the burning destroys the information? Why do we think that the epoxy preserves the information even though you can't open it, right? Why do we think the encryption preserves it? Well, for that, we need to turn to information theory, very light information theory, and the concept of an injective function. All right, so injective function is the one on the left. Non-injective function is the one on the right. What's the difference between these two? Well, this one keeps different things different. But this one does not keep different things different. 3 and 4 become the same thing. So in the case of burning the books, it's not injective, because if you have a pile of ash, you can't tell. There's many different books that could have made that pile of ash, and you can't tell which one is which. The rote 13 is injective, because you can always tell if there's 2 different books and you apply the preservation to them, then it keeps that difference, all right? So that leads to our first gold star idea here, which is preservation means that different things stay different, okay? That's what it means to preserve something. No matter how you transform it, as long as, in all cases, if the things are different, you maintain those differences, you will have preserved the information. That's what it means to preserve information. And that leads us to our second idea, which is interesting, that you don't actually have to understand what you're preserving in order to preserve it. For example, I can't read Chinese, but I can preserve Chinese books by using the epoxy method, because I know that if they were different Chinese texts, that the ink would be different. And I know that the epoxy doesn't alter the ink of the pages, and so different texts will make different plastic epoxy blocks. So this also applies to things like DNA. We were able to preserve DNA, even though we don't know what the DNA means, as long as you know that it's not going to change the letters of the DNA. Any questions so far? Yeah, what's up?
Probability of the preservation process. So, like, speaking quantum mechanics, you cannot destroy information. So the information is still there, it's just scrambled, it's impossible, it's very, very unlikely to recover it. So maybe you can preserve it, but maybe it turns out.
We'll do that. We'll do that one after. You have to have boundary conditions. So we'll do that later. Okay. So we'll do light information theory here. Okay. So moving on. So we know that if you're going to have information preservation, it means you keep different things different. Okay. Within a finite bounded volume of space and time, which is why you don't have the quantum mechanics. Okay. So now we're going to move on to clinical research. Okay. And this is one of my favorite clinical surgeries, and nobody knows about this for some reason. But the question is, if we could preserve brains, now we know a little bit more what that means. It means you have to keep different memory states different after you apply your preservation process. But the brain is a really complicated dynamic system. Like, my brain has a lot of electricity running through it right now, and a lot of chemicals running through it right now, and it's alive, stuff moves in it. So you might think, if you stop that movement, you stop that electricity, then, well, what does that do? Does that erase the information in it, or does it not matter? By default, it seems like maybe the brain works like a computer in a power outage. If you turn the power off to it, you would lose the information. Documents that are open that you haven't saved, for example. And so the question is, are memories stored in electrical activity, right? The actual functioning of the brain. Well, how can we figure that out? I think there's very powerful evidence that it's not, that comes from clinical science. So back in the day, maybe 100 years ago, doctors noticed that sometimes people will fall into frozen lakes. They have thin ice, you fall into it, and they'll drown in the lake. They'll literally drown to death in this lake. And they'll sit there for an hour, and you can fish the person out of the lake. And in this state, they have no brain activity. They have no heartbeat. There's no circulation. There's no breathing. There's no electroactivity in the brain. There's no electroactivity in the heart. They feel cold to the touch. They really look like they're dead. And yet, in some cases, if you warm them up just right, they come back to life and they function again with varying degrees of damage depending on how they drowned. So doctors noticed that this happened sometimes, and they thought they could take advantage of it by creating a technique called DHCA, which stands for deep hypothermic circulatory arrest. You see, there's this problem where if you need to do surgery on the blood vessels of the brain or the main aortic arch, we know how to do those surgeries. They're actually quite simple. The problem is the blood is flowing through these vessels, and if you try to do the surgery, then you're going to have blood go everywhere. You're going to have the patient die, and you basically can't do the surgery fast enough, even though you would know how to do it, to save the patient's life. Very unfortunate. These doctors noticed you could cool people down, and they said, well, what if we did that intentionally under a controlled situation so that we could make it so that the patient is cold, and now their blood isn't flowing. Now you've bought, they can stay under the lake for an hour. They sometimes survive that, so you've got an hour to do your surgery, and then you warm them back up, And maybe someone who would have died because you couldn't figure out how to physically do the surgery could instead live. So in the 60s, they invented this technique, and it works quite well. So they did a study for professional people to see if there was any change in their memories after cooling them down with this process and warming them back up. And the exact meaning of these is not so important. It's comparing people who had DHCA versus people who did not have DHCA. And it's judged by their boss and by their family in this case. And they just sent a questionnaire. Does the person seem different in any way than they were before? And they asked the family, I don't know, does dad seem like he forgot some stuff? And basically it said no. So it's quite amazing, but one of the very rigorous principles we get from clinical science is that memories have to be durable and physical constructs, whatever they are, and they clearly survive a shutdown, a total shutdown of electroactivity. Okay, so we know we need to keep different things different. We know memories have got to be some type of physical thing. The question is, what type of physical thing are they? To that, we need to turn to neuroscience. So let's go for what's our current theories of how memories actually work. So how does the brain create memories? Well, our current theory of neuroscience is this idea of memory consolidation, right? And this has been created over the last 40 years with a lot of heroic efforts in molecular biology and neuroscience. And so we found that memory consolidation has three components to it, essentially, three different timescales on which it operates. The first one is a minute or so, 1 second, 30 seconds, 60 seconds. And that really is controlled by the electrical activity in your brain. So think you're memorizing a phone number and you're trying to dial it in, or the exact words that I've just spoken to you kind of linger in an echo in your head for a little bit, but then you mostly forget. You don't remember exactly how I introduced myself, for example. So that's the short term, and we don't really care about that too much. Now you have this process that takes 1 to 2 hours that is kind of an intermediate process where there's been some changes to synapses, but the changes to those synapses are kind of liable. By default, they'll revert back to their original stage. This, by the way, is a synapse. So synapse is a connecting elements between neurons they use to communicate with each other. And synapses are quite complicated constructs, but they can change their size, and they can either do that temporarily or they can do it permanently. The temporary version is this 1 to 2 hour part. Then you've got more than 2 hours. And if you're going to remember something and you're able to remember it for more than 2 hours, it generally is encoded as a long-term memory. And it'll stay with you potentially your entire life. And when we look at what happens in the brain, we see that the synapses actually physically change. They actually change their size when a memory is created. So what does that look like? Well, it looks like this. So to provide the context here, these white blob things, okay, are these, right? This is about as good as can be done with light microscopy. And what you're looking at here is an actual living neuron, a tiny part of the living neuron and the synapses that are attached to that. And you're watching learning happen here. So this synapse in particular is going to enlarge. So you see that this is before learning, and then after the learning, it's bigger. And then over the next 2 hours, you know, it maybe reduces in size a little bit, but compare this one to this one, and you'll see that it got bigger. Now, synapses can decrease too. Look at this one here, and look at the corresponding one there. It's smaller. And the same thing with this one. That one's kind of small, but it barely exists here. So this happens in thousands of synapses throughout your brain, even to encode the most trivial memory if it's actually going to last for longer than 2 hours. One principle of the brain is that it's quite distributed. You can destroy any one synapse, it doesn't affect anything. Now, what does a synapse actually look like? They're very, very complicated, all right? They're very small. Your brain is about a liter of material, and a synapse is about a femtoliter of volume. So think about a trillionth of a liter, and then divide that by 1,000, and that's a femtoliter, okay? And so you have a quadrillion synapses in your brain. And so they provide the scratch space that you need by changing their size to store all of your memories. And even within that femtoliter of volume, you have about 40,000 proteins. And those proteins do various jobs, like moving vesicles around to release neurotransmitter, being the ion channels that control the strength of the synapse, and doing all of the housekeeping and maintenance to keep that synapse alive, and then also to be able to change the size. So very complicated constructs. But the main takeaway is that if you're going to create a long-term memory, you undergo the process of memory consolidation, and memory consolidation changes the size of synapses. And changing the size of synapses requires protein synthesis. We know this because if you inhibit protein synthesis, you can't consolidate memories anymore. It's actually kind of a weird effect. You can be under the effect of a protein synthesis inhibitor, and your short-term memory will work fine. That's electrical. Your medium-term memory will work fine. That's still doable because it doesn't require protein synthesis. But your ability to encode long-term memories is compromised. People have a very high alcohol tolerance, can get into this mode they call blackout drunk. And a person can be functional. They're blacked out not because they're unconscious, but because they're not encoding memories properly. And so you can actually have crazy situations where you could write yourself a letter or you could hide something somewhere while you're under the influence of this. You wake up the next day, you can actually genuinely surprise yourself and communicate with yourself this way. So we know that you have to keep different things different if you want to preserve information. We know that memories have got to be physical because clearly they survive a shutdown. And we know that if you're going to encode a memory, you've got to change synapses. So how does that come together to preserve memories? Well, that's why we have to talk about embalming. And the question clearly is, can you preserve synapses? Because if you could preserve synapses, you could keep different memory states different. So can we preserve synapses? Well, the answer is yes. We have long ago figured out how to preserve synapses since the 60s with a very special chemical called glutaraldehyde. Now, you might recognize the name. Glutaraldehyde sounds kind of like formaldehyde, right? And so, you know, formaldehyde is used in embalming. Glutaraldehyde often is too, although it's not talked about as much. And the way that it works is it's like a pair of molecular handcuffs. So each of these ends on here are called aldehydes, and it's got 2 of them. And what it does is it can cross cellular membranes, and it can grab those proteins. So all those fancy proteins right there. The glutaraldehyde enters. It's much smaller than that, and it glues them together. It gels them together into a solid gel and traps them so they can't move anymore. And it traps all the proteins into this gel. And so it's really quite effective at preserving the structure of a synapse. If you look at the protein content before and after preservation, it's identical. And here is what I consider a tour de force image from a very amazing paper where they did living imaging of a living neuron, and then they preserved it with glutaraldehyde, and they picked out exactly the part that they'd preserved, and they did electron microscopy on it. So this is what it looked like when it was alive, and you can see the synapses at the limit of what you're able to see on a living neuron. Then they looked at it with electron microscopy, and you're about to see what it looks like after it's preserved with glutaraldehyde, and image at a much higher resolution. It looks like this. And so you can see that every single synapse here is preserved, every single one of them. This looks exactly like just a higher res version of this neuron, which is amazing. You know, you've got a quadrillion synapses, but if you have one chemical that can glue all the proteins that they're made of together, then it sort of doesn't matter how many synapses you have, as long as you can provide that evenly to every synapse. So glutaraldehyde's clearly able to preserve synapses. That's why we've been using it for half a century to preserve synapses. So these are the 4 pieces, right? You have this requirement to keep different things different, and you have the knowledge of what differences are when you create a memory, and you have an incomparable preservation technique that's able to actually preserve at a much higher level of detail than is even required. If you imagine 2 copies of yourself, right, that are exactly identical to each other in every way down to the molecule, with one exception, that one single synapse in one of the brains of the people is changed, it's erased or it's enlarged, and you imagine what glutaraldehyde preservation would do, even a difference as subtle as that would be preserved by glutaraldehyde fixation. If you imagine 2 organisms that had one single actual memory different, that's going to be thousands of synapses at the very least, not just one synapse. And so, of course, glutaraldehyde would be able to keep those separate as well. So I think the analogy here is with DNA. DNA is something that we've only recently scanned. So the first Human Genome Project was in 2003, and we were able to scan the entire human genome at great expense. Out of curiosity, when do you think we knew enough about DNA to preserve the DNA? Any guesses? Come on, somebody be brave. What do you think? What year do you think we knew enough about DNA that we could preserve it, not scan it? What's that? Yeah, 60. So 1959, we discovered the structure of DNA. And once we discovered the structure of DNA, you can make a very straightforward chemical and thermodynamic argument that liquid nitrogen can preserve DNA, alcohol can preserve DNA, all kinds of things can preserve DNA. And so there were 50 years there where we were capable of preserving DNA, but we weren't capable of reading that DNA. But nevertheless, I think there's a compelling argument to be made that we should preserve the DNA of species that are going extinct from the 60s to now, because we can eventually read the DNA. And I think we're in the same place today with neuroscience that we were with genetics in the 60s. We know enough about memory that we can confidently preserve it, but of course, it's quite difficult to actually do anything with preserved synapses because there's an awful lot of them. But nevertheless, I think that this technology is the first in a series of a pipeline of technologies that will eventually lead us to a new era of history, the era of living memory. There you go.